Hello ladies and gentlemen, welcome to the final installment of your video lesson over Chapter 3, Section 2. This video is going to cover logarithmic properties and how to use them to solve equations. We have previously worked with exponential equations where we had one or two exponentials. In those cases we would either isolate the exponential and then convert into logarithmic form, or we would get to the point where we had an exponential on each side and those exponentials had the same base. So we would drop the bases and set the exponents equal to each other. Our approach with logarithms is essentially going to be the same thing. Why? Because logarithms are essentially just exponentials rewritten so that the independent variable is x instead of y. Anyway, so when we look at exponent properties, there are three exponent properties that we are going to be using here. In addition to our conversion. Remember that if we have an exponential in the form b to the x equals n, that is exactly the same thing as the log base b of n equals x. So we are able to convert back and forth using the definition of a logarithm. So anyway, we have three exponential or exponent properties that we're going to use here. You've got your product rule, your quotient rule, and your power rule. These three rules should look familiar. They're from algebra. The product rule states that if I have two exponentials with the same base and I multiply those expressions together, I should add the exponents. X to the a times x to the b is x to the a plus b. Quotient rule says that if I have two exponentials being divided, and I do x to the a divided by x to the b. Since the bases are the same, I can write that as x to the a minus b power. And then finally the power rule, which says if I take an exponential like x to the a and I raise it to the b power, I am supposed to multiply those exponents to get x to the a times b. As it turns out, all of these have an equivalent rule in logarithms. If I have a logarithm that contains a product, such as right here, the log of a times b, I can rewrite that as two separate logarithms, the log of a plus the log of b. So I can either separate or combine two separate logarithms using this rule. Quotient rule is very similar. It says if I have a logarithm that contains a quotient, a over b, I can rewrite that as two separate logarithms, the logarithm of the numerator minus the logarithm of the denominator. And the same thing can be done if I have two logarithms that have the same base and they're being subtracted. I can rewrite them as a single logarithm using this rule. And then finally we have the power rule version for logarithms, which says if I have a logarithm that contains an exponential, I can grab this exponent and move it out in front, giving me b times log of a. So I can pull that exponent out in front. Okay, so those are our three rules other than the definition. Now we're going to use those to condense and or expand logarithms. And then we're also going to use them to solve equations because they allow us to solve a whole other level of logarithmic equations that we otherwise would not have the ability to solve. So we'll start with, well, how do we use those rules to condense? So in example 1, number 1 here, we have a plus sign in between these two logarithms and we have the same base. So since we have a plus sign between these two logarithms, that tells us we're going to be using our product rule. Since the bases on the logarithms are the same, we can combine those into a single logarithm. So that would still be base 5 because the base is unaffected by this process. And then we would multiply x and 4 to get log base 5 of 4x. The second example, we have a subtraction sign in between, which tells us that we are using the quotient rule. Again, both logarithms are natural logarithms, meaning they have the same base, that base being e. So we are able to rewrite this expression as the natural logarithm of e to the 8th over e to the 3rd. Technically, that would be totally condensed. However, I'm really bothered by that. So I told the students today that they should keep reducing e to the 8th over e to the 3rd. You would subtract to get e to the 5th. And then there's also a property that says if I pull this 5 out front, that would give me 5 times the natural log of e. And this is equivalent to 1. So in my opinion, your final answer here should be that condenses down to the expression 5. Okay, the third one is kind of the exact opposite of that, though, which is one of the reasons why that second one bothers me. See, what we're supposed to do here is move this 4 inside the logarithm and make it an exponent, which would give us log base 2 of x to the 4th power. And again, all three of these are examples of things we would do if we were solving a logarithmic equation. So it's not really super important that you be 100% comfortable with, okay, it says to condense, what do I do? That's not the important part. The important part is that you are able to use those properties to manipulate equations. Okay, now when we go to solve logarithmic equations, those are going to come in two basic forms. You'll get to the point where you will only have a logarithm on one side, in which case your next step is to convert into the other form. And you will run into equations with a log on both sides. Most of the time, the bases will be the same. So that would read A would be equal to B. And if that's the case, then it's like an exponential. If the bases are same, you can drop the logarithms and simply change it to x equals y. Now, the one thing you cannot do, and this is a very, very, very important note here, okay? You cannot do anything to this expression here. There are too many logarithms, okay? You would need to combine those logarithms first into a single logarithm using the product rule, and then you could drop the logarithms. Okay, you can't cancel out the logarithms until you have condensed the left side of that expression down to a single logarithm. Okay, so that brings us to our solving examples, and again, we're only going to have two types. Either they'll have a logarithm on one side or a logarithm on both sides. So let's do some examples. Here in example 2, it says solve the following equations. Check for extraneous solutions when necessary. Now, what does that mean? Well, that means what we need to keep in mind here is that the number inside the logarithm has to be greater than 0. So n, the number inside the logarithm, must be positive. Okay? You cannot have a 0 or a negative number inside of a logarithm. They do not exist. So on letter A, we need to recognize the product rule here. We have two logarithms. They're both base 10. There's a plus in between. So we need to realize that that can be rewritten as the log of 3 times x plus 4 equals the log of 5x minus 2. Now at this point, we only have one logarithm on each side. Those logarithms have the same base, so we can drop those logarithms. They cancel. Then we would solve the remaining equation, which would simply be distributing the 3, which would give us 3x plus 12 equals 5x minus 2. Then we would isolate the variable, which would be subtract 3x from each side and add 2. Would give us 14 equals 2x. And then we would divide by 2, which would give us our potential answer, x equals 7. Now, the check for extraneous solutions bit is very simple. We need to take that 7 and examine whether or not these expressions are positive when we plug in 7. So 7 plus 4 is 11. That's a positive number, so that's not a problem. And 5 times 7 minus 2 would be 35 minus 2, or 33, which is positive. So checking the answer simply means make sure that when you put x back into the original equation, there are no negative numbers or zeros inside of logarithms. Okay, on to example B. We should see this negative in between and realize that this can be written as the natural log of x plus 1 over 3x minus 5 equals the natural log of 7. So we can rewrite it using our quotient rule and put the left side of the equation into a fraction. Remember that whichever logarithm comes first, that inside becomes the numerator. Whichever logarithm comes second becomes the denominator. At this point, the logarithms can be dropped, leaving us with x plus 1 over 3x minus 5 equals 7. To solve that expression, we would multiply each side of the equation by 3x minus 5 to dispose of the fraction. So that would give us x plus 1 equals 7 times 3x minus 5. That's a very simple equation to solve. We would distribute, which would give us x plus 1 equals 21x minus 35. Isolate the variable by subtracting an x and adding 35 to each side. Would give us 36 equals 20x. Divide by 20. And we get x equals 36 over 20, which reduces to 9/5. And again, we need to check that number against the original problem. We need to ask ourselves, if I plug in 9/5, is either one of these negative? Well, x plus 1 would be 9/5 plus 1. That's definitely positive. That would be 14/5. And 3 times x minus 5 would be 3 times 9/5, which would be 27/5, minus 5, which would be 2/5, and is still positive. So the answer would be 9/5. Okay, next example. This one is an example where we have a plus sign in between, so we should be multiplying. That would be log base 3 of x plus 2 times x minus 3 equals log base 3 of 14. Now it doesn't matter whether you drop the logarithms first or FOIL first. You're going to be foiling once the logarithm is gone anyway. So you might as well drop the logarithms right now because there's only one log on each side. Then you have to FOIL this expression here. Okay, this gets FOILed. So that would be x squared minus 3x plus 2x, which would be minus x, minus 6 equals 14. Should be relatively fluent in quadratics by this point in your pre-calculus class, so I'm not going to explain that any further. If you have questions, email me or come see me. Okay, we're going to subtract 14 from each side because it's a quadratic equation, which means if we want to know whether or not it factors, we need it to equal 0. So we have x squared minus x minus 20 equals 0. That does factor two numbers that multiply to negative 20 and add to negative 1 are negative 5 and positive 4, which means we have two potential answers given by setting those factors equal to 0. That would be x equals 5 and x equals negative 4. Again, we need to check those numbers against the original problem to see if they work. Anywhere there's an x, we need to check. So when we do that, we discover that 5, we get a 7 here, which works. X plus 2 would be 7, and x minus 3 would be 2. So 5 works just fine. That is a correct answer. But negative 4 does not work, because when I plug in negative 4, log base 3 of negative 4 plus 2 does not exist. Which means that is an extraneous solution and we throw it out. So the only answer to letter C would be 5. Okay, on to letter D. We have a negative sign in between those two logarithms, which means we can combine them into a fraction. Natural log of x over 3 equals 2. Now this is where this problem is different from the others, because there's only one logarithm here. Well, we discussed right before we started this section how when we only have one logarithm, when we only have a logarithm on one side, we are going to convert into exponential form. So we are going to take that expression. Remember that expression says log base e of x over 3 equals 2. And we're going to convert it into e to the second power equals x over 3. That disposes of the logarithm and allows us to solve for x by multiplying each side of the expression by 3, which means our answer is x equals 3e to the second power. Now, much like pi, there's absolutely no reason to put that into the calculator and get a decimal that we would then have to round off. We can just leave it in terms of e. And that number does work in the original equation when we check, because 3e squared is positive, which means it'll work just fine in that equation. Okay, next up on letter E, you'll notice that this 1 is sort of hanging out on one side. It's not contained in a logarithm. In this situation, what you need to do is get all of the logarithms on one side of the equation. So that would be subtract log base 2 of x from each side, which would change this equation into 1 equals log base 2 of x plus 7 minus log base 2 of x. Now it looks like the other problems that we have done, it has a minus sign in between, so we would rewrite the equation as log base 2 of x plus 7 divided by x. This only has one logarithm, so we would then convert that into 2 to the first power equals x plus 7 over x. Then to solve for x, we need to multiply both sides of the equation by x, which would give us 2x equals x plus 7, and then subtract x from each side to get our possible answer of x equals 7. Again, we need to take that value in our head at the very least and check it against the original equation to see if there's any problems plugging that number in to create a positive number inside the logarithm. There is not. That is the correct answer. Finally, on letter F, you'll notice the different part is that this 3 is sitting in front of the logarithm. So your first step is to use the power rule to manipulate that 3 into the logarithm. You're going to move it in and it becomes an exponent on that 2, which means you're looking at log of x plus log of 2 to the third power, or 8, equals the log of 2x minus 7. Then we've got a plus sign, so our next step would be to rewrite that as the log of 8x equals the log of 2x minus 7. Those logarithms would drop out at this point. Then we would continue to solve by moving the 2x, and that would give us 6x equals negative 7. Divide by 6, and we are looking at x potentially being negative 7 over 6. Again, we have to check that against the original equation, and in both of those logarithms, that value does not work because the log of negative 7 over 6 does not exist. So we had to throw out our only possible answer, which means the answer to this question, and this does happen, not super often, but it does happen. The answer to this question is no solution. Okay, so again, you have a very unique homework assignment attached to this. It's actually a mixed review of the entire section 3.2. There are 9 questions in each column on the homework assignment. Your responsibility is to complete one column of that worksheet. In theory, you're supposed to partner up with another student in the course, have them complete the other column, and then you're supposed to check your answers against each other because the answers in each column are the same for each numbered problem. Number 1 in the column 1 is the same as number 1 in column 2. Number 3 in column 1 has the same answer as number 3 in column 2, and so on and so forth. Thank you very much for your time and attention. We will have a quiz next week.